So what is been given is there is a cone which is made up of two materials. I'll just draw quickly. So like this is there. Okay. Okay. And outside of
Sir, there is a lag coming. Sir, you can switch off your video camera. Maybe it will help.
okay. So this radius is R1 and this radius is R2. So temperature here is given as 100 degrees Celsius. 100 degrees Celsius, and the temperature here T1 is given as 200 degrees Celsius. And it is made up of two layers. So there is a layer 1 and layer. So this is, let's say, 1 and this is, let's say, 2. This thickness is 0.15 meter and this thickness is 0.2 meter. R1 is given as 0.18 meter and R2 is given as 0.08 meter, and the thermal conductivity K1 is given as 5 watt per meter degree Celsius and K2 is given as 2 watt per meter degree Celsius. Okay, so this is what the question is, correct? So there is a frustum of the cone is been given. So this is a conical surface which is cut at both the ends. So here we are seeing it from the radial direction and therefore we are only looking at a triangular type of shape we are seeing. But if you look at in a axial direction, you will see a circular structure. Okay. So this is just a frustum of the cone which is made up of two material, layer 1 and layer 2. Correct. The temperature outside the layer 1 is given as 200 degrees Celsius. The temperature on the left hand side of the material 2 is given as 100 degrees Celsius. Again, the radius of radius R1 is 0.18 meter, radius R2 is 0.08 meter. Thickness of the conical part 1 is 0.2 meter, whereas the thickness of the second part is 0.15 meter. Now what we wanted to do here is first part A is we have to find out the temperature distribution in the layer. Temperature distribution in both the layers. Okay, correct. So what we have to do? What we have to do here, we are looking at the temperature distribution in both the parts, and clearly the heat transfer is taking place in a radial direction where the surface area is going to change as we move from left hand side. So let's say just for a simplicity, let us assume that the our x is in this direction. X is in this direction. Okay. So exactly on the right hand side of the layer 1, x is 0, whereas on the left hand side of the layer 2, the x is 0.15 plus 0.2, so that becomes 0.35 meter. Okay, clear? So in order to find out the temperature distribution, first we have to make the shell balance. So please make the shell balance. Please make the shell balance and find out the equation for the temperature, differential equation for the temperature. So there is no generation, there is no accumulation term is given. So please make a shell balance. Are you all solving or not? I am not able to see, but please,
So we're trying.
please make it. Yes, good, good. Thank you. So you can select a shell at any distance x from the right hand side. Isn't it? Consider the radius at that location being r. So the area is going to be pi r square, isn't it? And the corresponding flux is going to be QR. Corresponding flux is going to be QX because the heat transfer direction is in the X direction, isn't it? So QX is going to be the flux. So rate of heat input is going to be area, that is pi r square. Q out be again pi r square QX at X plus delta X, and that should be equals to 0. That should be equals to 0. So after rearranging, what you should able to get is d by dx r square qx equals to 0. That is what you are expected to get. So shell balance in this case, let me just write. So input is going to be area into flux at x. So that becomes area in this case is pi r square into flux is going to be qx at x. Output is again going to be pi r square qx at x plus delta x. So input minus output equals to 0. Input minus output equals to 0. So based on this, what we get is r square qx at x minus r square qx at x plus sorry, x plus delta x equals to 0. We can divide this entire equation by delta x. So what we get and rearrange. So what we are going to get is r square qx at x plus delta x minus r square qx at x divided by delta x, and that should be equals to 0. Again here you can see I am not getting rid of r square because r is going to vary as I move from a location x equals to 0 to L. Remember, so L, the entire distance is L. This entire distance is L, L, but we are moving from this direction, right to left, right to left. Okay. So as I move from right to left, depending on whatever the value of x I am having, my radius is going to vary because my structure is kind of a cone, isn't correct? And as I move away from the right hand side end, my radius is going to decrease. So on the right hand side, my radius is R1, whereas when I move to the extreme left at the distance of L, my radius is R2, correct? My radius is R2. So now from one, sorry. So from one, we can write d by dx, d by dx r square qx equals to 0. Counting the Fourier's law of heat conduction, what we get is d by dx, d by dx, dx equals to 0. So qx here will be minus k dt by dx. So doesn't matter k and minus sign we can get rid of because right hand side is 0. So k we are assuming constant. See, depending on whether the shell is in the first layer or in the second layer, in both the layers individually it is going to be the constant, but in a different layer it is going to vary, isn't it? So that factor anyway we will account later on. So up to this everybody is okay? Are you all able to follow what we are doing so far? So just by rearranging what we are going to from this equation, if we integrate it, what we are going to get is r square dt by dx equals to C1. So this becomes dt by dx is given as C1 by r square. This is equation number 2. Equation number 2. Okay. Now C1 we can find out subsequently based on the conditions, but let us look at this equation 2 more carefully. Remember here I have not got rid of r square, isn't it? Because r and x is related. They are not independent, isn't it? Unlike the previous case in today's class, we have taken r out from the bracket, but here we cannot take this r outside of the bracket because r and x are related. If I go back and see the figure, you will understand why I'm saying this. So as you can clearly see, as I move along the x direction on the left hand side, my r is decreasing. So clearly my r and x are related. These are not independent. So I cannot get out this r from this bracket. Okay. So let us find out how r and x are related. So just by looking at the geometry itself, we can find out how r and x are related, isn't it? Correct. So r and x, these are the straight lines. These are not the curve, isn't it? So clearly from the geometry itself, we can write down how r and x are related. So the radius at any location x I can find out from the geometry. So from geometry, I can write down this r is given as r1. So that is the radius on the right hand side. R1 minus R2. So that is the difference between both the radius, and this difference takes place over the distance of L. So that becomes L1 plus L2. Correct. So this is nothing but L1 and this is nothing but L2. Okay, L1 plus L2 multiplied by x. So this bracket is going to give me the slope in which my radius is going to decrease as my length is increasing from 0 to L, isn't it? Correct. And that slope is multiplied by x will give me the radius and the decrease, and that decrease I have subtracted from R1. So this is just from the geometry. This equation number 3 is just from the geometry. We can find out the relationship between these. So we can put all the values here. So R1 is given as 0.18, 0.18 minus 0.08 divided by 0.2 plus 0.15 into x. So what we get from this is 0.18 minus 0.2857x. So just check whether this is correct or not. Equation number 3. Just check whether this equation number 3 is correct. Is it correct? Hello? Hello, friends.
Yes, sir, it is correct.
Okay.
Yes,
So
sir.
then let us move to now our job is very simple, because now we can go back to equation 2. We can put r in terms of x and integrate, isn't it? We were not able to integrate equation 2 further because one variable was x and another variable was r, isn't it? But now we know the relationship between r and x. We can put this in equation number 2 and we can integrate. So dt by dx, again I can write down from equation 2, now we can write down dt by dx is given as c1 divided by 0.18 minus 0.2857x square. So now we can integrate it, isn't it? So after integration, what we get is, dt is given as integration of c1 dx 0.18 minus 0.2857x square. So what we get from this is t is obtained as 3.5 c1 divided by 0.18 minus 0.2857x plus c2. Check whether this is correct or not. So this is, we can obtain both these for this is, let's say, block 1. So for block 1 the distance is going to be 0 to x 0.2 meter, and similarly for block 2, this is for block 1, For block 2 also we can obtain the same expression. So that I can write down as T2 is again obtained as 3.5 C2 divided by, sorry, let's use another constant here, 3.5 C3 divided by 0.18 minus 0.2857x plus C4, and this is between the range 0.2 to 0.35. Is it correct? Both the equations are correct.
Yes, sir.
Still solving, sir.
Okay. So now find out C1, C2, C3, C4. All the boundary conditions you know, isn't it? When x equals to 0, t equals to t1. When x equals to L1 plus L2, L1 plus L2 that is 0.35, then temperature T is equals to 100 degrees Celsius. So, and on the top of that, in between, at the boundary of layer 1 and layer 2, minus k dt1 by dx should be same as minus k2 dt2 by dx. Correct. So the continuity has to be maintained at the boundary of both the layers. So you have all the equations available with you. Find out C1, C2, C3, C4. So please find out the C1, C2, C3, C4. I'm writing down the boundary conditions. So boundary conditions are boundary conditions in this case are going to be when x1 equals to 0, T1 equals to 200 degrees Celsius. This is the first boundary condition. When x equals to 0.35, T2 will be 100 degrees Celsius, and another boundary condition is going to be at x equals to 0.2, T1 should be equals to T2, correct? And the fourth equation you require in this case is going to be for continuity K1 dt1 by dx equals to minus K2 dt2 by dx at x equals to 0.2. Okay, so you have four conditions and four constants. Find out. Find out the four constants. Is somebody recording the video? Okay, yes. Sorry, I forgot to record. Okay, good. Thank you. Anybody got the values of constant C1, C2, C3, C4? I am writing the values of constants C1, C2, C3, C4. Just check whether these are correct or not. We will not go ahead unless you confirm whether these are correct or not. Okay. So C1 minus 2.119, C2 241.2, C3 minus 5.297 and C4 is 331.74. Okay, so are you all getting the same value? Just check. Just check whether these values are same or not. K1, K2 are already given. K1 is 5 and K2 is 2 watt per meter degree Celsius.
Yes, a similar order.
Similar order means this should be nearly the same value. Of course, the last two digits, if you are varying, it's okay. But are you all getting the same values?
Yes, sir.
Everyone?
So C3, I'm getting a positive sign in C3. Otherwise, the value is same. Maybe
C1 you are getting negative and C3 you are getting positive?
Yes, sir.
Not possible.
But the value is same. Maybe I have done some calculation error. I will check.
Because C1 and C3 both are related. K1 C1 is same as K3 K2 C3. If you look at the equation, you can clearly see that relation, isn't it? K1 C1 is same as K2 C3. So if C1 you are getting negative, obviously C3 will also be negative. Just check. So is it correct? All these values are correct. Can we go ahead? Can we go ahead?
Yes, sir.
So with these values, if you put these values in the equation, finally what you are going to get is the temperature distribution. So temperature distribution based on this value is, I am writing the equation. Just check whether you all are getting the same equation or not. So 41.2 divided by 1 minus 1.587x. So this is for 0 to x between 0.2. Okay. Similarly, the temperature distribution for the second block is going to be T2 will be given as 331.74 minus 103 divided by 1 minus 1.587x, and this is between 0.2 to x 0.35. Okay. So check whether you all are getting these answers or not. These are remember in part A we were interested to find out the temperature distribution in layer 1 as well as layer 2. Correct. So these are the answers for part A. Just check whether you all are getting the same or not. Is it same?
So can you scroll up the sheet?
I scroll up. Okay, just wait. This one.
Yes, sir. Just scroll a little bit more. Okay, sir. Okay, it's fine. Yes, sir. We are getting the same.
Okay, so that is the part answer of part 1, part A. If you go back and look at the problem statement for the part B is in part B we have to find out the rate of heat flow through the assembly. So we have to find out capital Q. Okay, so Q we have to find out. So how we can find out Q from this? Can anybody? How we find out the Q in all geometry? So heat flux into area remains constant, isn't it? Heat flux into area remains the constant. That is what also we have seen here. If you go back and check, remember this equation is what? dt by dx is so this r square dt by dx, this is going to be into k. If you multiply here r square dt by dx, if you multiply k here, that becomes your flux, isn't it? That becomes
Yes,
sorry, k dt by dx is your flux and r square is there. So you, if you multiply pi, then that pi r square is the area into k dt by dx, that is the flux, that is going to give you capital Q directly. So from equation number 2, capital Q can be written as minus pi k1c1, isn't it? Minus sign will be there because flux will be minus, isn't it? Minus k dt by dx, isn't it? Correct. So if I write down from equation number 2, if I write down this part B, in part B we can write down this as pi k1c1. So this is not wrong, isn't it? We can write down again in another way pi k2c3 also, isn't it? Am I right? Is it correct? Is it correct?
Yes, sir.
So now we know C1 and C3, you can put anything, whatever you are comfortable with. K1, K2 you already know, and find out Q. So that is the answer for part B. So based on this, it is minus 3.14 into K1 is 5 watt per meter, and C1 you have already calculated, that is minus 2.119. So this becomes 33.3 watt. Check whether you all are getting the same answer or not.
Sir, how did you write this pi kc?
Just go back and see the balance equation. Sorry. Just go back and see the balance equation. Where is the balance equation? Balance equation we are having here. Look at the equation number 2. dt by dx we are having minus k dt by dx is what? Flux. And flux into area at any location is going to remain constant because Q is going to remain constant. Whether I am looking at the Q at the right hand side or on the left hand side, capital Q is going to remain constant, but small q, the flux is going to change, isn't it? But that flux multiplied by area, that total multiplication is going to remain constant, isn't it?
Yes, sir.
So if I multiply dt by dx by minus k here, my minus k dt by dx is going to become my flux into area into area is going pi r minus pi C1 from equation 2. Correct? Is it correct? Are you able to get it?
Sir, your voice broke in between, but is it something like minus pi k dt by dx minus pi k c1 by r square?
I'm doing it here directly.
Okay.
Okay. Am I audible now?
Yes, sir.
Q is flux into area at all x, isn't it? So flux becomes minus k, so that becomes minus k C1 by r square into r square. So this becomes minus a C1 pi. Am I audible? Hello, am I audible?
Yes, sir, you're audible.
So is it clear now?
Yes, sir, it is.
Okay. So this is what I have done, and in a similar manner you can obtain the equation in terms of C3 also. But then in that case you will have to multiply K2. So K1 C1 is same as K2 C3.
Yes, sir.
Okay. Let's move to part C. Part C is what? We have to find out in part C. Part C, we have to find out the heat flux at the open end of layer 2. Okay, so heat flux Qx at x equals to L, we have to find out, isn't it? So part C, in part C, we have to find out Qx we have to find out Qx at x equals to 0.35. Correct. So what will be Qx at the, so this is going to be Q divided by area at x equals to 0.35. Correct. Q we already know 33.3. Area at x on the left hand side, that is going to be pi r2 square. Pi r2 square, isn't it? So we can just put the values here, 0.33, sorry. The radius is 0.08 square. So what we get is, can anybody find out the values? Can anybody tell me the values? This is it correct?
Yes.
Okay. So we can move to the next part based on this. So part D, let's move to part D. Now in part D, what is the question? In part D, we have to find out the temperature at the surface of contact, isn't it? If I go back the statement, the temperature and heat flux at the surface of the contact of the layers. So where the layer 1 and layer 2 are in the contact point of layer 1 and layer 2, we have to find out the temperature as well as flux. Okay, so temperature we can directly find out from the temperature distribution, isn't it? So temperature distribution T1 we already know. T1 we can write down as 241.2 minus 41.2 divided by 1 minus 1.587 x and this x should be what? Equals to x should be equals to 0.2, correct? So if I put the values here, I should get the temperature T1 at the boundary. So 1 minus 1.587 into 0.2. So that comes out to be 181 degrees Celsius. Just check whether you all are getting the same. Are you all getting the same?
Yes. Yes, sir.
Now again, what you are interested in finding the flux Qx at x equals to 0.2, correct? Qx at x equals to 0.2. So that means you have to find out this Q divided by pi r square, and this r square should be at x equals to 0.2. So find out r at x equals to 0.2. So r is related to the x, and that relationship we have already written, isn't it? So that becomes 0.18 minus 0.2857 x, isn't it? So x here, x is 0.2. So what you get is, from this what you get is r is obtained as 0.1228 meter. Just check whether you all are getting the same value or not. So this is the r at the contact point. This is the r at x equals to 0.2. Okay, now put in the equation. So qx at x equals to 0.2. We can directly write 33.3 divided by pi. So that becomes 3.14 into 0.1228 square. So this becomes 702 watt per meter square. Check whether you all are getting the same answer or not. Are you all getting the same answers?
Yes, sir.
Yes, sir. 703.
That's perfectly all right. 702, 703, depending on how accurately you have used the values, is perfectly all right. So is it clear to everybody? Can we stop today?
Yes, sir.
Yes, sir.
Okay, then see you on Thursday.
So from the next time onwards, can you upload the tutorials by Friday or Saturday so it gives us more time to solve?
Sure, I will definitely do that. I have all the tutorials made with me, but definitely I will do it early. No problem. Yeah. Okay.
Thank you, sir.